We'll start the session at 6:10 so that late we'll let others also join. Till then, if you guys have any question related to the previous weeks, you can ask me, no issue. Okay, so we'll start the session. Hello everyone, I'm Balram Shah. I'm the PMRF TA for this course, that is Optimization Methods for Civil Engineering. I'm doing my PhD at Interdisciplinary Center for Water Research at IISc Bangalore. So today we'll be discussing about the lectures that you have gone through, or maybe whichever you are doing in for week 7. So week 7 lectures, we'll be doing some assignments, questions, and then we'll be going through the all the lectures that was there in week 7. Okay, so today we are going to jump from the one part of this optimization methods to the other part. So in the first part, that is till week 6, what all we have discussed about the classical optimization as in using the calculus or some search method, maybe gradient based methods and all, right? So we'll be moving from the classical optimization method to something known as meta-heuristic methods or optimization methods. So we'll be coming to that, to the meta-heuristic methods later. But before that, can you just list out that what are the limitations in the classical optimization method in the calculus or gradient based methods, or any assumptions that we have made in the classical optimization methods? Okay, so before that we'll go to this directly. Fine. Oh, sorry. Okay, so I'll stop sharing here so that I can start sharing here. I hope you can see the screen fine. Okay, so as I mentioned, today we'll be discussing about the week 7 lectures of the course, that is optimization methods for civil engineering. So till now whatever we have dealt with comes under the broad topic, that is classical optimization method. So in classical optimization methods we have started with uh, calculus, how to get to the optimum, maybe global optimum or local optimum, what is stationary points. So in that we have seen that how to get to the which is the global maximum or which is the global minimum for unconstrained problem. So when there is no constraint, only the objective function is there, in that how to deal with the optimization problem. Then we have also seen constraint optimization such as there will be several constraints to the objective functions that we are going to solve or we have solved. So in those, the constraints can be uh, equality type or non-equality type, maybe less than equal to type or greater than equal to type. So these things we have done using calculus. Then we have gone for several search methods like gradient based methods, then Newton-Raphson method, some numerical methods to get to those. In those we have made some assumptions while doing those. Okay, and which comes as the limitations of those methods. So we'll list out those limitations first. So in the whatever classical optimization methods we have seen, the functions, the objective functions, those objective functions that we have seen, those functions should be continuous and differentiable, right? So we have seen, and we have also seen what is continuity, what is differentiability and all. So I'm not going very detail on all those. So we have seen that the function should be continuous and differentiable, right? So there should be, if there is any discontinuous function, then we can't use the classical optimization method, right? If there is any function which is non-differentiable, then also we can't use this kind of optimization method. Also, what we have seen, that those algorithms that we have seen, algorithms as in methods, those methods are not suitable for solving the discrete optimization method, right? Also, uh, while doing that, we have seen that we can reach to any kind of let's say if there is one function, so we are so in the okay, in the last we have not used this. So if there is function something like this, so this is, let's say, is the global minimum, right? So using those variables and all, we get to, let's say, x or x mean, whatever x star we are getting as, let's say, 3.25. Okay, so what we are seeing, that whatever we do, we get to the non-integer kind of problems. So these algorithms are also not suitable for integer kind of problem, or let's say mixed integer kind of problem, for integer or mixed integer problems, right? So let's say while designing a dam, okay, so while designing a dam, you are getting let's say the maximum cost as maybe I'm just not a dam, let's say something you are designing, and we are getting some cost as 325.43 rupees. Okay, but in the real scenarios, in the practical application, we can't just give say, or for the design or for the whoever is doing the policy, we can't say that we need 325.43 rupees. We have to get to an proper estimate. We have to get to the let's say round of figures, maybe let's say 330 rupees or 350 rupees, something like that, right? In the beam problem also, in the, let's say, in while doing the structural analysis, you are for a one beam you are designing that, and you got that the optimum value whatever you will get, you are getting at a depth of, or at a depth of maybe 3.26 meter. Okay, but you can't let's say you have a reinforcement and you are getting the diameter as, let's say, 8.5 meter 8.56 meter millimeter. So you will not get 8.56 millimeter anywhere, right? The diameter, so you have to either go to 8 millimeter or 10 millimeter. So based on the practical applications, we can't get this kind of integer we can't directly solve this kind of integer problems using this classical optimization method. So other than that, what all we have assumed, we have assumed that the function should be convex in nature, right? Or let's say we have also seen how to work with the concave problems, right? So the problem should be either concave or convex. Okay, so let's say when you are searching for minimum, you are working on convex problem, so there should be only one mode, right? Only one global optimum should be there. It can be global maximum or global minimum. So this is one of the big assumptions that we have did. So let's say if you are having some function something like this, right? So in this, you see here we have one maximum, here we have one maximum, here we have one maximum. So we have three maximums, but we have only one global maximum. Whereas again, if you see, we have here one minimum, here we have one minimum, here we have one minimum. So we have one global minimum here, right? So this one, the last one, is the global minimum. So in these kind of function, we have not used the classical optimization method, right? And other than that, while using any kind of this kind of algorithms, let's say any gradient based algorithms, what we have seen, we have to consider one initial point. So we were considering x naught, something like x naught equals to 0 or something like that, right? So so we have to consider one initial value, some initial value we have considered. So now let's say there is some hill kind of thing. So this is like hills, and you are here, let's say you have started climbing the hills from this point, that is A, right? Now you are climbing and you will reach some optimum here, and you will say, okay, with the classical optimization method, that this is my global maxima, or let's say maxima, right? But again, if you consider some initial point as B here, then again that algorithm, what it will do, it will keep iterating and you will reach this maximum, right? So this one will be another maximum, right? So from this, what we understood, that whatever initial value we are taking, based on that our results might change if there is any function which is not convex or concave. So if we have several modes, then it can lead to different solutions, right? So for all this, what we can do, we can use some meta heuristic methods. Okay, so what is meta heuristic methods and what all those are, we'll reach to that then now. Okay, so here what we have seen. Okay, so these can be for any kind of classical optimization method. So now we'll move to the, so now what we are doing, we are jumping from the classical optimization method to meta heuristic methods. Okay, so introduction to meta heuristic methods. Firstly, what is this meta heuristic method or methods, whatever? Okay, so this word, that is meta heuristic, you have two words that is there in this, that is meta and heuristic. So this word meta means above, or let's say beyond any point. Okay, so with meta, what we are doing, we are moving to another level, that is we are going for higher level. Okay, and next is heuristic. So heuristic means to find. Okay, so how we are finding, we are using some search methods maybe, and we are keep iterating that, so that we are reaching to the optimum. Okay, so most of these meta heuristic kind of methods are nature based. Okay, so these are mostly, so whatever algorithms we'll be seeing are nature inspired. Okay, so in the first class, maybe introduction to optimization, also we have seen several nature based optimization, right? Optimization problem we have seen that, let's say when you are when flock of ants are moving and you are keeping one bar here. Okay, I'll draw that. So let's say these are my ants. Okay, something like this, and you are putting one block here. Okay, as they move here and they are seeing that there are no space left, what they will do, either they will move in this direction, some of them will move in this direction, and some of them will move in this direction. Okay, and then based on whatever is shortest distance for them, and they will, after some time, you will see that the ants are taking that path. Okay, so they are also, they are considering some optimization method. So this is one of the nature based. Why it is not working? Oh, sorry. Okay, I don't know why it happened. So what I was saying, so these kind of behavior is also seen in nature. I don't know why it's not working. Okay, so in the nature, what we see, from long back, if you see, mostly whoever is the fittest one, they survive, right? So they, what we do, we survive, so that we can survive. So we keep competing with others so that we can survive. So as the Darwinian theory is there, that Darwinian theory of survival of the fittest is there, right? So there are several aspects with which we are learning, and then we'll be using those algorithms in this kind of methods. Okay, so there are several aspects like competition as in we have the best one will be there. Okay, or whichever is the fittest will survive at the end, right? So there is one point of survival of the fittest. These all the let's say we as a humans or animals, all of them, what we are doing, we are keep learning, because as I said in these and examples, they are also after reaching to that block, they are moving in the two direction, and then they are seeing that which direction is the shortest, and then they are moving in that kind of direction. Okay, so they are also what they are doing, they are learning, right? So after that, we are having communication. Then we are having swarming as in many of the animals or many of the living creatures, if you see, they stays in groups. Okay, so like bees, and then let's say wolves, or maybe birds, while they are at a very high level, they will be flocking in a in a group, right? So that kind of swarming aspects we will see. Okay, then we have reproduction, so that it will go generation to generations. And as we have seen that we not only us as a humans, but animals and every living creatures, maybe plants and all, they are also keep so evolution is there. Okay, so for this we have different algorithms. Okay, so some of the most commonly used algorithms are genetic algorithm. Then we have particle swarm optimization. So these two methods, whatever are there, these are evolutionary method, because evolution, whatever is evolution that we have discussed, mostly that is the basic principle for these kind of methods. Okay, then we have different so these genetic algorithms and particle swarm optimization. With the particle swarm optimization, what we have seen, if you have seen birds like in a very high altitude, they will be flocking something like this. So let's say these are birds. Okay, and the first the one this one, mostly you'll see that all of them are not flapping their wings, but some of them, one or two of them, will flap on their wings for some time, and then they will be moving in that direction for a long time. Okay, so these kind of techniques that they use, so that they can optimize their energy. In this case, in the bird flocking case, they are optimizing their energy so that they can reach at a very far distance. Okay, so these kind of technique we'll see particle swarm optimization. Other than that, we have different algorithms, such as differential evolution is there, then firefly algorithm is there, then we have invasive weed optimization, ant colony. So if anyone would have seen the Ant-Man and the Wasp of the Marvel movies, in that also they have mentioned, or you might have seen. Okay, so there are ant colony optimization, then ant leon optimization, several other optimization methods we have learned from the nature. Okay, so today we'll be discussing mostly about this genetic algorithms. Okay, and then we have simulated annealing. So annealing you might have heard about in the metallurgy, or maybe materials people will understand that this what annealing, you might be knowing that annealing is the process in which materials are raised to raised at a high energy, right? They will be raised to a high energy levels for melting, and then it will be cooled to its solid state. This process is called annealing. So will be this simulated annealing is also a process which with which we can optimize. Okay, okay, so what we were discussing, about the metaheuristic methods, right? So mostly in the classical optimization, what we have seen, we'll be doing step by step procedure. Okay, so first we'll be coming at one point, and then again moving to the other point, and then so in that we go stepwise. But in this methods, that is metaheuristic methods, it is mostly inherently parallel. So parallel processing kind of thing will be happening, and in that case, in the case of the classical optimization method, what we have seen, we know the functions. Okay, other if we don't know the functions, we can't move, because let's say we don't know the objective function, then we can't optimize. But let's say in this we know the features, but we don't know the function, then also it's fine. So that is called as non-knowledgeable or non-knowledge based, let's say. Okay, I'll write like that. I don't know why it's not working. Okay, what is, I don't know, it's not working. So non-knowledge based optimization. So even if we are not sure about the nature of the function in this kind of methods, we can work with it. Okay, so in this, so let's say even if you have a function with it's not it's not required that it is convex or concave. It can have several local optimum and one global optimum, right? So in that case also, it's very easy to discover the global optimum. Okay, and this methods avoids the can avoid trapping in local optimum, because in the last methods what we have seen, what happened, in this method what we have seen, that if you consider one initial value, then you will stuck at the whatever local optimum is that next to it. Okay, but in these kind of methods, that is introduction to metaheuristic methods, whatever is there, and these metaheuristic methods, it avoids it avoids in the local optimum. You will not be get trapped in the local optimum, but you will reach to the global optimum, because it sees the whole search space. So we'll see that how it is seeing and all. Okay, can you see? Yeah. So generally what we see, whatever population we have, population as in, we'll come to that. So with this population, all the population as in whatever initial values we are taking in the functions, you consider here a population. Okay, so population, what the population do, it struggles for existence. As I said, that it struggle for its existence. So from there comes the theory of survival of the fittest, isn't it? And after whoever who all fittest survives, what they do, they reproduce and they propagate their inherent information or whatever characteristics they have developed. So whatever favorable characteristics are there, they will propagate to the next generation. So these population will reproduce and will propagate their information. With information, I'm saying their propagate favorable characteristics. So with the information, I was saying the favorable characteristics that they have achieved during the evolution or during their struggle for existence. Okay, and with this we'll get the evolved species. Evolved species as in the next generation. So in the real world, let's say in the human or any animals, these are keep repeating, because otherwise the generation will stop, right? But in our work we'll stop that, terminate the work. Why? We'll see, because anyway we have to reach the optimum, right? Okay, so using this theory, what it comes the principle of the natural selection. So this one was the principle that whatever we have seen is the principle for the natural selection. So in this way we select the next species or the evolved species. So with all this, what we understood, that we have to select the best and we have to discard whatever is remaining, discard the rest. Okay. So using this principle, that is principle of the natural selection, we'll be moving on to the one of the evolution algorithm, that is genetic algorithm. But this genetic algorithm is also kind of search method, but it is not like only random search is there, but there is one guided kind of search. Okay, we'll come to that. Okay. Okay, so as I was mentioning that first, so before that I'll explain both whatever I have mentioned. That is, first one was the random search and second one was the guided search. So in random search, what we do, so let's say for example you are given 4 letters. Okay, so let's say the 4 letters are L, A, G and O. Okay, so with O is not happening. So we have 4 letters, that is L, A, G and O. With this, what is the objective function? The objective function is to make a word that is called goal. Okay, so in random search method you are giving this 4 letters and you are given these 4 letters, as in you don't know which. So you have 4 cards, let's say, right? Now you have to just take that 4 card without seeing that what is written on those cards. You have to arrange it such that it forms this word, that is goal. Okay, GOAL. Now let's say you are randomly selecting some cards. So some cards, as in you are randomly selecting the letters. So in the first iteration, or maybe say trial 1, you are getting something like GLOA. So first card shows G, second card shows L, next card shows O, and last card shows A. Okay, but and then you are seeing that okay, now it is not possible, like the objective function you have not reached. Okay, now again you have to do randomly select this. Okay, and you are not given, again the cards are randomly shuffled, and then you have to get to the objective function. Okay, or let's say you are these 4 letters are given in 4 cards and you are blindfolded. Okay, now you have to choose, and at the end someone will tell you, okay, that whether you have reached the objective function or not. So whether you have made goal as the proper word or not. So GOAL is not there or not. Okay, that information will be given again. Till the time you are not getting the objective function, you will keep repeating or keep iterating. Okay, so let's say in the trial 2 again you got some other combination, that is GOLA, let's say. Okay, in the trial 3 you are getting something like AOLG. So this is random. Okay, you are not getting any information other than whether the last point that you are getting or the objective function you are getting or not. That's it. So this can have n number of trials. Okay, so this is proper random. So we'll do several iterations unless and until we reach the objective function. Okay, next is the guided search. So in the guided search, what we do, we provide you with additional information. So in the random search, what we have seen, the trial 2 and trial 1 are not having any relation. This means you have first given GLOA. Now if you know that okay, the first letter that was there is G, then you have to only arrange last 3, right? that information is not given. So by any means there is no relation or there no interrelation between any of the trials in the random search method. Whereas in guided search method you are given more information, some additional information, so that you can reach to the objective function very fast. Okay. Now so here what I was saying, we are given some additional information after each iteration. This means what? So let's say in the trial 1, in trial 1 you got maybe what to say, okay, so in the first trial you got AOLG. Now here if you see the second letter, that is O, is at the correct position. So in that iteration someone is telling you or someone is giving information that okay, the second letter that you have put is correct one. So now as you are getting additional information, you are guided by someone. Okay, so the next search that you will do will be only based on the first letter and the remaining last two letters, right? So in that case that is called as guided search. Okay, so in the guided search, if let's say if letter is placed in the correct location, then information will be provided that okay, this is the correct place, so that you reach to the optimum very fast, right? So this is called guided search method. So random search method and guided search method, I hope it's clear for you. Okay, so in this Darwin's principle of natural selection, what we saw, that members with maybe higher adaptive character will flourish. Okay, so whoever has higher adaptive capability, they will flourish. Okay, so they will, okay, I'll write that. So with Darwin's principle of natural selection, so why we are studying all this, we'll come to that. This is one of the method for selection. Okay, so whoever has more adaptive character, it will flourish. So those can only reproduce, they can inherit the characters from their progenitors. Then there will be variability of characters, so all the characters will not be the same but different. With this what I am meaning, that there will be diversity in whatever species that are getting reproduced. Okay, so there will be mutation, there will be diversity in the whatever species that have reproduced. Okay, for example, let's say some people who are staying in Himalayas. Okay, so those, they are at higher elevation that than ours. Okay, so we know that as you move up in the altitude, your oxygen level will be reducing, but the people that they are staying, who are staying there, have adapted that feature, that at low oxygen level also they can survive. Low oxygen level as in some less than that of whatever we are staying. Okay, so they are having that adaptive feature so that they can stay in this mountainous region. So those people who can't survive in those region will either move back or to some location where they can survive. So in that region, whoever can survive with low oxygen level can is the fittest one. So they will only reproduce there, they will inherit their characters into their offsprings. Okay, and there will be variability of characters among those offsprings. So with all this, we'll move to the genetic algorithm. Okay, so genetic algorithm was given by Holland or John Holland in 1975 in some book. Okay, so what is genetic algorithm? These genetic algorithms, I'll write is as GA, are heuristic search method, or let's say heuristic search optimization technique, which mimics the whatever we have seen, the natural selection. This principle, this method mimics the principle or the process of natural selection. Okay, or maybe natural evolution, let's say. This genetic algorithm implement the optimization strategies by simulating the evolution of species using natural selection. Okay, so in the genetic algorithm, mostly what you will see, there will be one simple procedure. If you see, you will start with some population. Okay, you will start with some initial population. Okay, so with this population, what I meant, there will be several set of solutions. Okay, so you will start with some initial population, and then you will evaluate these solutions so that you can get some improved solution, right? Now with this improved solution, you'll see whether you need to terminate the process or not. Okay, if you are terminating, this means okay, fine, you have reached the optimum solution. But there are several ways that at what point you have to terminate the process. Okay, so there are several process. Some operators are selection operator, then crossover operator, and then mutation operator. So with all this, at next time step you will see, and then again you will see whether to terminate or not, and you will keep iterating unless until you get the optimum solution. Okay, or optimum population. So let's say here, how we code the solution using some chromosomes. Okay, and these chromosomes, or the initial population that I have mentioned, this initial population is selected based on what? Selected based on a fitness function. So these fitness functions, so will in initial value also, in some of the methods what we have seen, we have just considering some initial value. But while considering this kind of initial population, what we will do, we'll see some of the solutions. Okay, and in those solution, whoever whichever population exceeds the, let's say, the fitness value or the fitness function, here this fitness function is called the objective function. So whoever reaches this fitness function or exceeds this fitness function, will consider that as the initial population. Okay, so then we'll see the fitness function, which is the objective function here, and then with this we'll generate the initial population. And after that, anyway, I have mentioned in the here, what we'll do, we'll select the parent chromosome for reproduction. Okay, so now we are selecting the parent chromosome for the reproduction, and then we'll use this kind of techniques, that is, or the operator, selection operator, crossover operator, mutation operator, to terminate that at what point we have to terminate. So other than these operators, simply also we can terminate if let's say if it is not very complex functions or complex problem. Then what we can do, we can see, okay, will not go for any kind of operator, but let's say I am only happy with 100 iterations or 1000 iterations. So some functions you have given, and you are doing some optimization, and you are saying at 1000 iterations will stop. So that can be one of the termination criteria. Other criteria can be, let's say, you are doing iterations and iterations, maybe 150th iteration you are doing, then you are keep repeating the iteration, you are getting 151th iteration, and like that till 150 to 160. You are seeing that in all those you are getting the same value of optimum value. So in that case also you can stop, right? So in this methods, that is in genetic algorithm methods, whenever you see that there is no change in any some of the features of the offsprings, then you will terminate there. Okay, so other than these small thumb rules are there from which you can consider to terminate. Okay, otherwise we go for this kind of mostly we use this because we have computational power nowadays, so we usually go for this kind of operators, that is selection operators, crossover, mutation operators, and so on. Okay, so what is the function of this? So as I say, these are the operators. So we'll be seeing these operators and some of the methods to get to these, use these operators. We'll see that. Okay, so what are the functions of this selection operator, or let's say function of operator? First function is to identify the good solutions, or let's say not for, in a population. So with this function, what you will get? So when we are identifying the good solution in a population, this means we are selecting the parent distribution. So this is the selection operator. Next, we have to make multiple copies of the good solution. Okay, so that we can reach to the optimum value or optimum whatever we are doing. So in this we are doing the mutation. So this will lead to the mutation operator. Next function is to eliminate the bad solutions from the population. From the population. So what we are doing? So now we have the next solution, let's say. So we have a set of solutions again. So we have population again. Now from that we have to eliminate the bad solutions. So here we do the crossover or use the crossover operator. Okay, some other operators are also there which we can use. So in the selection operator also, in selection method, we have different operators. For mutation we have different procedures. Okay, so as I said before that, before going to this operator to terminate, we see the initial population, and for selecting the initial population, what we do, we use the fitness function, which is the objective function in our case. So some fitness value will be assigned to evaluate the solutions. Okay, so let's say there is some function where some function, let's say f, where you have to minimize the cost of one product. So let's say a cylinder. So in that case you have to minimize, let's say, the cost into that surface area. Okay, so you will choose the population such that it follows this function or this value. So if it is maintaining this fitness value, then only you can consider that as a initial population. Okay, so let's say this is for cylinder, and here we want to minimize the cost, right? So with this minimization also, we can go for maximization also. So we can write maximization value as 1 by 1 plus f. Now one question can be, why we are using 1 by 1 plus f, why not simply minus f we are using, right? So in these kind of cases where we are using this, mostly whatever function we'll have or the fitness value we'll have will not have negative value. Okay, so let's say in the case of this, cost cannot be negative, right? So what we will do, we'll consider some function so that we can reverse that. So while doing some of that method, we have used one inverse operator also, remember? So here also it is kind of inverse operator. Now if let's say f, the function value is 0, minimum whichever it can have, so this fitness value can be 0 or more than that, let's say. So in that case maximum is, so the minimum value of that maximum function will be 1, because if f is 0 then it will become 1. Okay, and if f increases, right, then what will happen, the value will decrease. Okay, so this is simply the, we can use this for converting from min to max or max to min, something like that. Okay, so this we use mostly in the genetic algorithm. Okay. Okay, after that what was there, let me check. So after that we come to the parameters. So these operators or parameters we used for selection. Okay. Okay. Okay, so this fitness value or this fitness function, what they do, they quantifies, sorry, quantifies the optimality of the solution. Okay, so we'll consider those population only which are very near to the optimal solution. Okay, and then we'll consider that initial population, and as we mentioned in the last one, so this one is kind of table. So then we'll evaluate the next solution. If the next solution is maintaining this, following these kind of operators, then it's fine, or else we have to do it again on that operator till that time we are reaching the optimal value. Okay, fine. Okay, so coming to the operators, this first one was selection operator. So now to use this selection operator, we have different techniques to implement this selection in the genetic algorithm. Some of them are tournament selection. So in tournament selection, what we do, so let's say as the assignment questions today are not more with more calculations and all, I'm just covering the whole part first, all the 3 lectures, and then we'll be moving to the assignment questions, because it will not take much time. It's simply, if you know all the theories, you can answer the questions. Okay, whatever. So first one is the tournament selection. So in the tournament selection, what we do, so let's say we make tournaments. So as we have seen that we are considering some initial population. Now we have a set of solutions, that is population, and we have a set of populations. Now what we'll do, we'll make some tournaments between these populations. Okay, and whoever will be the fit one, will consider that as in the next iteration. Okay, so in the lectures, if you have seen, they are he has considered one cylinder problem, and then you have seen that some of the cylinders or the sum of the cylinder values are having maybe 22, let's say. Some is having, let's say, 32. Okay, so in this, whatever maximum is there, we'll consider that solution, that is 32. Okay, so this is what, this is tournament among two of the populations or the two of the solutions. Okay, and like this we'll make tournaments of twos. Okay, and then what we'll get, and we'll keep that for two kind of tournaments we'll do. Okay, and from there, whatever will be the optimum value we'll get, we'll take those two, and then we'll have the selection. Okay, so what we do here, so in the tournament selection, so let's say you have some examples, I'll give like that only, maybe 13 or 40, then 7 and 25, let's say. Okay, so in the second round, who will win? 41 will win, and in this we'll get the 25. So this one was the tournament among two of the solutions for the first match. Similarly, we'll do a second match, let's say, of, let's say, 32 and 25. So we'll just randomly select this, Okay, so this one was the first match. Now whoever has won the first match, that is 32, 40 and 25, okay, will first consider those. Okay, so now 32 and 25, if you see, what you have to do, you have to minimize the cost. But here, okay, so based on whatever function you have, you will get to those. Okay, so based on that, let's say you are getting some of the copies. First one is, let's say, 22, second one is maybe 32, then maybe 25, then again let's say 32, okay, then again let's say maybe 25, then 13 was there, right? So these are the copies that you got after the matches, right? Now what we are seeing, that after two matches also we are getting two best solution here is, let's say, 32, okay. uh, so after two matches what will happen, so what we are doing, tournament among two will do, okay, and from this what we'll get, we'll get the best solution. So best solution will have how many copies, best solution will have two copies, because we are doing for two tournaments. So in the two matches or two tournaments only, who will win, the best solution, whoever is there will win, right? Now now in the two matches, the whoever is the worst solution, so in the first match it has lost, in the second match also by some means, if let's say we are getting to those, in that case also that will get rejected, right? So the worst solution, or the maybe worst solution, will have no copies, okay, and then whatever other solutions are there, other solutions can have the maximum number of copies, how many matches we have done. So let's say if we have done 5 matches, okay, of two like we are doing tournaments among two, and we have done 5 matches, okay, so other solutions can vary from 0 to 5, okay. So in this case other solution can have, sorry, 0, 1 or 2 copies, okay. I hope it's understood. Okay, so this is one of the selection procedure, selection operator, that is tournament selection. Next is the roulette wheel and proportionate selection. So this is one of the very easy method which you will see. So as I said in the last one, so we consider some chromosomes for let's say some, when you're working with genes and all, okay. So we have, let's say you have several populations and you have then checked the fitness value. So for first population you got chromosomes fitness value as I'll write that. So let's say you have different chromosomes, okay. Chromosomes is numbered as 1 2 3 4, let's say 5, okay. Now you have the fitness value also. So first one is 50, second one is 6, let's say, then 36, 30, 36, 6 is 28, whatever he has explained in the class, I'll take that example only so that it is easy to understood. So the sum of this fitness value will be how much, 186, okay. Now what we'll do, we'll calculate the contribution of each of the chromosome for the total matches, okay. Not matches, let's say the total fitness value whatever is there, will check the contribution of each of the chromosomes, okay. So how many number of chromosomes are there? There are total 6 number of chromosomes. So the total fitness value, if you add all these fitness values, you'll get as 186. Now the contribution of the first chromosome to this total fitness value is how much, we'll calculate that. So how we'll calculate that, we'll just calculate the percentage of the roulette wheel. So percentage, how we'll calculate, we'll calculate 50 by 186 into 100. So with this you'll get something like 26.88. Similarly you'll get the contribution of each of those. Okay, 3.23. So I'll write after that, you can just do it. 19.35, 16.13, 19.35 again, and 15.05. As you are seeing the contribution or the percentage, total will be 100. Right. Now you have the contribution of each of the chromosomes for the fitness, for the total fitness value. Now you will just create a wheel. Okay. Now whatever contribution is there for each of them, you can just draw the pie chart for that. So this pie chart is very, it is not to scale. Okay, so it can be like this and this, like this. So this one is the first chromosome, let's say this is the second, this is the third one, this is the fourth one, fifth one, and sixth one. And what you'll do, we'll rotate the wheel, and you'll see, let's say if some of the chromosome has very high fitness value. In that case, what will happen, if you rotate it several times, most of the time whoever has the highest number of fitness value, let's say all these are 36, 30, 28, 34, 32, something like that, but one is having, let's say, 90. So that fitness value is much higher than whatever proportion others have, other chromosomes have. So in that case, if you are creating one roulette wheel and you are keep repeating the iteration, or you are um, moving that wheel again and again, most of the times what you will get that chromosome, or the chromosome which will have the very large fitness value. Okay, so that also we have to remove, because let's say if you are doing this method and every time you are getting the same chromosome again and again, so in that case you will not have diversity in the solutions, or you will not have diversity in the populations or the offsprings that you are getting. So we have to consider diversity also. So in that case, what we have to do, we have to change that fitness value such that will not get that again and again. So we don't want to saturate the things. So we want to have diversity in our offsprings. So in that case, what we will do, we'll see that how we'll do that. But just to note that if any chromosome has very high fitness value, so in that case we can't just consider that, because it will saturate the offsprings. After some iterations, only that chromosomes will come. Okay, so we don't want that, we want diversity in it. Okay, so in this case, what we'll do, we'll rotate the roulette wheel, and we'll get that at what point we are getting, like at some iterations we'll get some of the chromosomes, and we'll note it down, and so that it will be the next iterations solution. Okay, so similar to this, using this percentage of roulette wheel only, we go for this proportionate selection. So I'll not write this again. So these three are there again. So let's say chromosome, fitness value, and percentage of roulette wheel. I'll write this only. So we got it as 26.88, 3.23, 19.35, 16.13, 19.35, 15.05. Okay, now what we'll do, we'll get the expected count, or in that you mention as EC. Okay, so how we are getting this expected count? Can you just tell me? So I'll write this 1, 2, 3, 4, 6. The values were 56, 36, 30, 36, and 28.
Sir, you are asking us how we are calculating expected count.
Yeah,
Are you
correct,
asking?
correct.
Then it is multiplied by the number of candidates, I think.
Mm. Yeah, multiplied by the number of candidates, as in
Hello.
Hello. Multiplied by
Yes.
number of candidates, as in give me some just one example that how you are getting this expected count.
That is weightage of each candidate. That means uh, total is 200 means first candidate 50 means 50 by 200.
So total is 186. Now you tell me how we are.
0. Point,
Sorry.
total is 186.
Hmm.
Weightage of each candidate we will get that value of for first candidate divided by total value.
So with that we got the percentage of the roulette wheel. That is
Yes, sir.
26.88. Now we want
Yes, sir.
expected
It
count.
is 0.268. 0.268 multiplied by, if candidates are 4,
Hmm.
0.268 multiplied by 4, we will be getting expected count.
Correct. Okay. So what we are doing? So our percentage how much? 26.88 by 100,
Percentage,
right?
uh,
So
yes, sir.
into how many number of chromosomes we have? So how many number of chromosomes we have? We have 6 number of chromosomes. Okay.
Yes, sir.
So if you do this, how much you'll get?
0.2688 multiplied by 6.
Yeah. So you'll get something like 1.6128,
Yes, sir.
right? So like this, we'll
Yes, sir.
calculate the expected count for each of those. Something you'll get something like
Yes.
0.19, 1.16, 0.97,
Thanks.
1.16, 0.90. If you add again this, because we are doing for one proportion only, percentage only. So if you add all those, because we are multiplying that with the number of chromosomes, the total should be the number of chromosomes only, because we are giving weights to each of the uh, counts, right?
Yes. Yes.
Now we'll have the actual count, because as I said, it can't be just a decimal value, or like point value, right? So what
It
we'll
must
do,
be called.
so we'll consider it as a integer, or the whole number. Okay, so 1.61 can be considered as 2, this can be considered as 0, this can be considered as 1, this can be considered as 1, this is 0.97. Okay, this can be considered as 1, this 1. So total will be 6 again. Okay, now as I said, there can be some some situations when there is very high number, high value of the fitness for some of the chromosome. So in that case, just for example, let's say chromosomes you have, fitness value you have, I'll write all those fatafat. uh, Expected count and actual count, it is again, let's say 6 are there. 86, 20, 25, 10, 18. Now you see the fitness value for the first chromosome is much higher than the other chromosomes that you can see. Okay, so if you calculate the percentage, you'll get something like 54, 13, 16, 6 and 11. Okay, expected count is 3, 0.2, 0.8, 0.9, 0.4 and 0.7. Actual count is 301, 101. Okay, so before that, why we were doing that expected count and actual count, this we were doing for the proportionate method. So from there we can say that okay, the first one has the actual count of 2, and the next is 0, then 1, 1, 1 and so on. Okay, so we'll have higher probability for this chromosome, that is chromosome 1. Okay, now if you see the using this roulette wheel for the next example, example number 2, let's say, if you see the percentage of roulette wheel also, or if you see the actual count also, what you are seeing that for the first chromosome it is having much higher percentage, that is 50% in case of roulette wheel. And if you see the rest of the chromosomes, that is 4, 13, 16, 6 and 11 you are getting, right? In that case, what is happening, that after some iterations you will get only the first chromosome, so we'll reach the saturation, we don't need that. So in that case comes the rank selection. Okay, so what we do, we rank it. Okay, so what we do, let's say we'll give the rank to each of these. Okay, so so whoever has the highest percentage of our roulette wheel, or maybe higher number of actual count, we'll consider that as the highest rank. Okay, so let's say first one has the actual count of 3, it is the highest of all those, so it will be given rank of 6. Okay, like that you will give. Okay, no, sorry. Okay, not to here, to the next one. So we have 6 chromosomes. We'll do it based on, first we'll, what was the chromosomes were 1 2 3 4 5 and 6. Even if you don't see the percentage of roulette wheel or actual count, you can even after seeing the fitness value, you can see that okay, this one is having much higher value, much larger value, so we have to do the rank selection. So what we'll do, uh, so, so the fitness value was 86 and all this. So now we'll give the ranks to it. So what all are there? 80, then 6, 20, 25, 10 and 8, right? So the first one is having the highest one, so this will have a rank of 1. Second is who, 25, so this one will get 2. Am I doing correct? Wait. Okay, sorry. You have to first arrange it based on the fitness value. Okay, so what we'll do, we'll arrange this fitness value. We'll arrange this according to their fitness value. Okay, so the fitness values, if it arranged in descending order, it will be 80, then 25, 20, 18, 10 and 6, right? So if you write the chromosome number values just for those, it will be 1 4, then 3 6 5 and 2, right? Now we'll assign the rank for it. Okay, so the first chromosome got the highest rank, the the fourth chromosome got the second rank, the third one got the fifth rank, this got the fourth rank, like that. If you just write, and 2 got the rank number 1. Okay, and then after arranging to the rank, using this rank only, again you can do the percentage of roulette wheel or the proportionate method that we have just learned. Okay, if you do that, percentage of roulette wheel, how much you are getting, 6 by total will be how much, 11 11 4 15 15 3 18 18 20 21, 6 by 21 into 100, how much you will get, 6 by 21 to 100, you'll get something like, okay, I'll write that 6 by 21 into 100, you'll get something like 28.57. So like that you need to calculate the percentage of roulette wheel, and then again whatever we have seen in the last methods, you can use that. And then you will see that after, because we are now working with ranks only, we are not using the fitness value, we have just, what we have did, we have replaced the fitness value with the ranks. Okay, it is uh, showing the same picture that fitness value was showing, but with some other values we are just working. Okay, so after working with this rank, what we will see, we will not have the saturation, you will have the diversity in the offsprings. Okay, and that's why we are use this rank selection method. So we'll write here, this one was the rank selection method, this one was also one of the selection operators. Okay, so with this what we have done, so with the when we are discussing about the functions of the operators here, so first function was to identify the good solutions in a population. So with all these procedures or methods that we have seen, we can, what we can do, we can select the good solution. So the first function is done. But the next one, that make multiple copies of the good solution, so that we have not done yet. So for that we'll use the crossover operator. Okay, so in crossover operator mostly we use the encoding method, that is the most commonly used method. So what is encoding? Encoding is simply so let's say you have some chromosome. Okay, chromosome something like this. Okay, now what we are doing, we are converting this chromosome into a string. Okay, so string can have different characteristics, and then we are converting this string, that is the chromosome, or let's say this information is called the gene. This gene we are transforming into the maybe some of the some way, so that we can understand or the computer can understand the whatever information is there in that chromosome. So for that mostly we use the binary operator. So let's say it has 0 1 1 0, sorry it will not start from 0, okay, whatever. Okay, so now we have what we have done, we have done the encoding of the chromosome. So this chromosome, what we did, we have just represented the solution in the form of a string that can convey the information that is present in that gene, so that we can understand. Okay, we or maybe the computer can understand. So for that only we have converted. So this conversion is called the encoding. And if you again get back to that, then it is called as decoding. So generally we use the binary encoding. Okay, so this, let's say, just for the mm, sake, maybe some binary number is there, 10100. Okay, so this is the encoded one. We need to know the uh, proper solution to it. Okay, so how will you get this? So just converting the binary number to a decimal number, what you'll do, you'll just multiply this with the 2 to the power of those. So if you go from the right hand side, it will be like 0 into 2 to the power 0 plus 0 into 2 to the power 1 plus 1 into 2 to the power 2 plus 0 into 2 to the power 3 plus 1 into 1 into 2 to the power 4. So this one represent 2 to the power 0, this one represent 2 to the power 1, this one represent 2 to the power 2, this one represent 2 to the power 3, and this one represents 2 to the power 4. If you sum up all the products, then you will get the decoded value. So 2 to the power 4 into 1, you will get as 2 to the 4, 6, 2 to the 4, 4 to the 8, 8 to 16. And others whoever are 0, even if you multiply that by anything, it will be 0. So we'll only consider this, and okay, that's it. So it will be 20. Okay, so 10100 means what? 20. Okay, similarly, if you want to get to the binary number from the decoded one, so let's say 20. Okay, we should get 10100. How we'll get? We'll just divide it by 2, 10. So in this there is no remainder, right? So we'll write 0. Then 2, 5, there is no remainder. 2, 2 to the 4, there is remainder of 1. And 2, 2 1 the 2, there is no remainder. And then we'll move to the from the back. Okay, so how much we are getting? First one is 1, then 0, 1, then 0 and 0. So see, you got the 10100. I hope you understand how to convert the binary to decimal and decimal to binary. Okay, this is simple only. I'm not giving much time to this. Okay, so with this what we do, we first consider whatever population we have. So let's say if you are considering one chromosome, so whatever information that chromosome is having, we are representing that solution in the form of a string, and this string is represented in a binary form, and this process is called encoding. Okay, now what we are doing, we'll use this encoded binary bits to get to the uh, crossover operator, whatever you were discussing. So what I was discussing was the crossover operator. So the most popular crossover, it selects any two solution strings randomly from the mating pool. So we have a mating pool where, let's say, reproduction is happening and all. So in that, some portion of the string is just exchanged. So let's say if you have two strings, maybe two chromosomes you have, and then what you're doing, you're converting that into a string, and you're considering one crossover site. Okay, so let's say this site is called as the, let's say, the crossover site that you have considered. Okay, so now let's say this string looks like something like this. First string, this is called, let's say, parent 1, and this is called parent 2. So what we'll do, we'll just exchange the information after the crossover side or before the crossover side, based on your whatever you want. So what we are doing, we are exchanging the part from the first parent to the second parent. So we are just exchanging. So the child, how it will look like, so same strings it will have, let's say 2 childs we are having. Okay, now the at the crossover side, whatever information before was there, it will be similar, and now this information, that is this one, will go to this and this one will come to this. So here it will be like this, but in this it will be like this. So this one is the child 1, this one is the child 2. It can be written as offspring or what. Okay, so in this we just exchange between the things, we are doing exchange. Okay, and then we are having the child. So this is one of the crossovers. So in the binary crossover, what we will do, so let's say we have 2 binary bits. So as I mentioned about the cylindrical thing, we have diameter and height. So let's say you have 2 bits. Okay, first one is having, let's say, 4, and second one is having 5. So it will be like 1 1 1 0. Second one is here I will make 1 0 0 0 1. Okay, now what you will do, so we have 2 binary bits, let's say, sorry, something like this, 1 0 0 0 0 0 1 0 1. Okay, now let's say this is the crossover side. Now before this we'll consider whatever as it is, and then in the next one it will be changed, it will be 1 1 1 0, and then after this whatever is there after that crossover side will come to this 0 0 1 0 1, and the next child will be 1 0 0 0, and from first parent it will come 1 0 0 0 1. Okay, so in this we have done the binary crossover. What we are doing here is binary crossover. So with this, what we can do, we can make multiple copies of the population, right? Okay, next operator is the mutation operator, because in the function what we have seen, one operator should be firstly it should select the good ones, good solutions. Second, it should make multiple copies of the good solution, and then we have to discard the bad solutions from the next solutions that we have got. Okay, so in mutation what we do, we just change it. So let's say one binary strip is there, and it is like 1 0 0 1 0 0 1 1. Okay, we have different information here. Now let's say you have considered this bit, okay, and you want to mutate in this one. So what you will change, you'll change that 1 to 0. Okay, and with this what will happen, the information will change. With the information, what I mean, if this is the encoded version, now if you decode this, what you'll get, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, 2 to the power 7, 2 to the 4 4 8 8 6 32 64 128. So you'll get, if you decode this, you'll get 128 plus 2 to the 4 4 8 8 16, 16 plus 2 plus 1. How much you'll get? 14 16 17 1 2 4, something like this, 147 maybe. Okay, so now if you change this 1 to 0, so what you are doing, you are doing mutation on this one. So how it will look like, it will look like 1 0 0 0 0 0 1 1, right? Now if you decode this, you'll get something like 128 plus 2 plus 1 and 130. So see, the offspring that was, or the solution that we had has changed from 147 to 130. Okay, so in this what we have done, we have done the mutation. Okay, so we have changed the one binary bit to another one. Okay, so here what we are doing, what are you saying, So one of the main thing that you can see, if we are changing or if you are mutating the information from the right hand side, there is very less difference is there. See, if you will change this one, I'll change the color. If you change this one to 0, only value will decrease with 1 because it is 2 to the power 0, right? If you change this 1 to 0, only two values will two digits will be less. Okay, so what I want to say is, if you mutate from the right hand side of the binary information whatever we have. Hello, can you hear me properly? There is some issue with the मुझे पहले करना चाहिए था. Okay, whatever. Okay, so with this what I want to say is, if you change any binary values in the left hand side, it will have very high impact, whereas if you change in the very right hand side, it will have very less impact. So this crossover and mutation, it can discard the best solution of the population pool sometimes. So we use elitism.
Sir,
Sorry, yes.
could you please repeat? If we change the left hand side, high impact, right hand side, low impact. Is it correct, sir?
Yeah, correct. See how
Okay.
I will say. So let's say, if in the left hand side, the first one that you are saying, let's say this one, if you change this to 0, then what will
Yes, sir.
happen? This 128 will become 0, right? Then the total value
Yes.
will be 16 plus 2 19. So this
No.
147 will change to 19. So there is very high impact because it is changing
Oh,
from 147 to 19. Whereas if you change this, the right hand side for a number, let's say 120, then how much will change? Only one digit will change. It will change from
yes.
147 to 146. So that's why it will have very less impact. Okay.
Okay, sir. Okay, sir.
Now what we have seen, while doing this while using this crossover operator or this mutation operator, it can be possible that the best solution of whichever is there from the population, it can be discarded or it can be destroyed. So what we use the elitism operator. Okay, in this elitism, what we do, we preserve the few best solutions of the population pool. So while doing the uh, using the method or the evolutionary one of the any of the evolutionary method, what we do, we preserve some of the few best solution. We know, okay, these are the best solution, we'll preserve and use that population only for the next iterations. Okay, so we'll preserve this few best solution of the population pool, and then we'll continue the iteration. Okay, this elitism is just defined in maybe percentage or in number. So we are not going to that one. This elitism and all will discuss in the next class. I hope till this only he have discussed, maybe, right? Let me check how much he have discussed. I think till this elitism also he didn't discuss, I think. Yeah, okay, till this only he has discussed. Okay, so till now, is there any question, is there any confusion? Okay, if not, we'll go to the questions. Okay. Oh, we are in the sorry. Okay, so the first question, oh, can you you can see, right? Okay, so the first question is, gradient based optimization method is used for. So as we know, gradient based optimization method is one of the classical optimization method. So in that case, those methods should be continuous and differentiable, right? And it should be either convex or concave type of nature. It should have initial solution. So in this, only continuous and differentiable will be the answer, because even if it is differentiable, it is sometimes it is very hard to get the derivative value. So for that case, we use Newton-Raphson some numerical method so that we can reach, right? So mostly the gradient based optimization method is used for continuous and differentiable value. So answer is D. Okay. So the next question is, genetic algorithms involve which of the following phenomenon? So just now we have seen that in genetic algorithm the functions are to get to the firstly select the good solutions. Next we have to make copies of the good solution, and third was to discard the mm, bad solutions, right? So we use selection operator, we use crossover operator, and then mutation operator. So all of the above will be the answer for this, right? Okay, we'll move to the next question. Next question is, if the parent solutions are if the parent solutions are 1 0 1 0 this whatever, and the crossover site is 3, which indicates one of the new offsprings. Okay, so let's say 1 0. So first one is 1 0 1 0 1 1 0 1 1 0 0 1, right? Now we have said that crossover operator is site 3. Okay, now the parent solutions are, first one is 1 0 1 0 1 1, and the second one is 0 1 1 0 0 1. Okay, now it is mentioned that the crossover site is what, 3. So after 3 we have kept the crossover site. So in the crossover what we do, we exchange the information, right? So we'll just change this with this. Okay, so the new offsprings will be what? New offsprings will be 1 0 1 0 0 1. Next will be 0 1 1 0 1 1. Okay, so these two will be the offsprings. So then one of the new offspring is which one? 0 1 1 0 1 1. Huh. So B will be the answer, because 1 0 1 0 0 0 0 1 is not there. The answer will be B. Okay. So the next question is, genetic algorithms for optimization is most likely to succeed given a small population of fit and similar individuals. Okay, so what we have seen in genetic algorithm, we need to have a large amount of populations, because population itself will have a set of solutions, and then we'll consider several strings, right? Several chromosomes or several populations. So we need a large population, and as I mentioned that why we are not considering that some chromosome which are having very high value, we need to change that so that we can have diversity in our offsprings or the individuals that will be reproduced, right? So for genetic algorithm for optimization, it should have a large population and it should have diverse population. So correct answer will be D. Okay. Okay, so next question is, genotype in natural evaluation resembles with which of the terminology in the genetic algorithm? Okay, so there I have not mentioned. While we saw that chromosome, so what we are doing, we are converting this chromosome into an information or a string, right? And this string was coded with binary digits, right? So this string is called the, or this structure is called the genotype. Okay, so the answer for this genotype will be the resembles for the structure or the coded string. Okay, so correct answer will be C. Okay, whereas let's say every chromosome will have its own features, right? That will be called as gene. So this process is called the, sorry, this string is called the genotype, whereas the information that will be there in this will be the gene or the feature or the characteristics, let's say. So I think the next question is that only. Yeah, so the next question is, gene in natural evaluation resembles which of the terminology in the genetic algorithm? So it will be feature or the character. Okay, so answer will be B. Okay, so next question is, genetic algorithms are, what is genetic algorithm? Can you just read and tell me the answer? Maybe it can have more than one answer also, it's fine. You guys can put in the chat box also if you are having problem with audio. So as I mentioned that genetic algorithms, what it do, it consider it is one of the evolutionary method. So it is based on the evolution theory or the theory of natural selection. So this evolution and natural selection or selection of the best in a population of the candidate solutions uh, is considered as the basic principle. So this one is correct. Next is a method based on the theory of natural selection and evolutionary biology for solving optimization problems. Same. Next is a technique for genetically modifying ants to do ant colony optimization. So here what it is saying that genetic algorithms are the technique which genetically modify the ants so that they can do ant colony optimization. But it's not the case. Ant itself, they do the ant colony optimization. We don't do anything on the ants, or we don't put any algorithms on the ants so that it uh, do the ant colony optimization. It itself do the optimization. So this is not a technique, but the ant colony optimization that ant uses naturally, we considered that process in the genetic algorithm. I hope the message is clear. Okay, next line is a heuristic search method used in artificial intelligence computing. So we use this in, so answer will be all these three, A, B and D. Okay. Next question is, the genetic algorithm is suitable for parallel computing. As I said, it is inherently parallel. So it has operators like reproduction, crossover and mutation. It is a population based approach. It does not require gradient information of the objective function. It is a robust optimization tool. So see, gradient, while doing the parallel computing, firstly it does not for while doing the parallel computing, the genetic algorithm, we need a large population size. So mostly it depends while doing why we go for parallel computing. When we have a large number of population data set, or we have a large number of data sets and have different methods to apply on the same uh, kind of populations. So we do what we do, we send it to different cores, let's say. Okay, and we do the same processing in each of the cores. Okay, so in that what we are doing, it is a population based approach, right? So answer will be population based approach. Okay, next question is, the genetic algorithm is a powerful tool for both local and global searches simultaneously. A powerful tool for global search, powerful tool for local search, a weak tool for global search. So mostly we do it for global search only because we need the global optimum, not the local one. Okay, so it is a powerful tool for the global search. Okay, next question. Okay, there is some question. Okay, so the question is, let the population of the chromosomes in genetic algorithm is represent. I have not given the next question, I think. Okay, let the population of the chromosome in the genetic algorithm. Okay, the option, correct option is correct, coming up before the question. Fine. So question is, let the population of the chromosomes in genetic algorithm is represented by terms of binary numbers. So these are the populations that you can see. Okay, the strength of fitness of a chromosome in decimal form x is given by this. So this s of fx represent the strength of fitness. Okay, and it is given by f of x by summation fx, where fx is equals to x square, right? Now, so firstly you have to get to the fitness value, because what is the question? The question is strength of the fitness of chromosome this. So this is the second chromosome. So we need to find out the strength of the fitness of second chromosome. Okay, so first we need to decode all the chromosome, let's say. Why it is not writing? Okay. So the first chromosome, can anyone just decode this? How much we'll get? Oh, I'll write chromosome 1, 2, 3 and 4. 1 1 0 0 0 0 1 0 0 0 1 0 0 0 1. Okay, can you just tell me the decoded value? See if you do this. You can do it on your own mouth also, it's fine, but just to write like that. 0 into 2 to the power 0 1 2 3 4 plus 1 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. So you can just write whichever has 1, you can just write by counting. 8 plus 4 plus 1. This one will be 13. Similarly, if you decode all this, how much you are getting? 4 2 to the 4 4 is 8, 8 is 16. 2 to the 4 4 is 8, 8 is 16. 16 plus 8, 24. This one will be 8, and this one will be 16 plus 1, 17. Is it clear? This is simply conversion from binary to decimal. Okay, so the total value will be 14 7 7 14 14 7 21 22 7 में 1 2 5 6 2 2 4 2 6 62. Right? If my calculation are wrong, let me know. Now what we have to calculate? The strength of the fitness value, right? So just in percentage you have to calculate 13 by 62 is,
Should we calculate square, sir? There is something like x square.
yeah, so this is what, this is x value.
Square also we
Now
have.
you have to calculate fx, and then you have to calculate the s of fx.
Okay, sir.
Fx is what? 169. 24 into 24, how much? 576. 8 8 is 64. 289. Right, and summation is how much? 169, sorry, 169 plus 576 plus 64 plus 289. You'll get something like 1098. Now you have to get to the strength of the fitness, that is s of fx. Right? How you are calculating? You are just take this function, that is f of x divided by summation fx. I'll write here again, fx by summation fx. This is summation fx, right? So how much you are getting? 169. Okay, you just need to calculate the strength of fitness for the second chromosome. So it will be 576 by 1098. You'll get something like, okay, so it will be, sorry, it will be d 0.52. Okay, correct answer will be d. And just like that, you just calculate what will be for others. It will be 0.15. 64 by 1098, 0.06, 289 by 1098, 0.26. Should get 1.15 plus 0.52 plus 0.06 plus 0.26. Yeah. So if you take more decimal values, you will get to 1. So the correct answer will be this, because we only want to find out the strength of the fitness of the chromosome 11000, that is the second chromosome. Okay. Is it clear? Okay. Okay, so we'll move to the next question. Next question is, crossover is convergence in nature and mutation is divergence in nature. So is it true or false? Okay, answer is coming before. So as we say, as we saw that you, if you do crossover more times, you will get convergent value, because crossover, whenever you are doing, it will converge. But mutation, what it will happen, it will diverge. So uh, crossover is convergence in nature and mutation is divergence in nature. Next question is, for steady convergence, a high value of crossover probability and low value of mutation probability is to be used. So while doing this crossover, or using this crossover operator or mutation operator, what we consider is the probability value for both. In the crossover probability we have crossover operator, we have crossover probability, whereas when using this mutation operator you have mutation probability. So when we are doing crossover operator, we have high value of crossover probability, that is around 60% to 95%, maybe zero point 0.6 to 0.95. So in that case what will happen, it will have steady convergence, because let's say if it is at very high value, okay, and then if you are doing the crossover, then it will have very convergence in nature, right? And if you do mutation, and if you are having very high probability of mutation, then what will happen, it will diverge, right? So for that, mutation operator should have very low probability, right? So for this, answer will be true. Okay, so the next question is, the primary search operators in genetic algorithms are, so it is mentioned that primary search operators, okay, so it will be crossover and mutation. Okay, next is what, the next question is, the crossover operator in genetic algorithm requires, yeah, so let's say if you have only one solution, okay, so here it requires as in minimum how much it is required, okay, how many minimum how many solutions are required, because if you are having more you can do anyway. So in crossover operator what we are doing, we are just exchanging the information from, let's say if you have two solutions that you are exchanging, but let's say if you have only one solution, you can't operate this crossover operator on that, you can't exchange in this only, right? Otherwise the whole information will change. So you need at least two solutions to exchange the information or do the crossover operation. Okay, so the correct answer will be B. Okay, next question is, the mutation operator in genetic algorithms requires, again the minimum solution that mutation operator requires is how much? In mutation what we are doing,
One solution.
one solution, because we are changing in that solution itself. Okay, so we need at least one solution. Okay, so A is the answer. Next question is, suppose you are applying tournament selection and use a tournament size of 2, okay, then the worst solution the population pool will have, even if your tournament size is 2 or 3 or 4, okay, if you are doing that, the worst population will have no copies, okay, so it will have 0 copies. Okay, next question is, suppose you are applying tournament selection and use a tournament size of 3, then the worst population in the population will have, sorry, okay, so if you are having a tournament size of 3, so in the example what I showed, I have taken only two solutions, and then from there we got the whoever wins the match or maybe wins the tournament in that match. Okay, so in that case we have having 2. Now if you have having 3, then what will happen, then you will have, what's solution in the population? Okay, so question is wrong. Okay, sorry, this will not be worst solution, the best solution will be how many, because yeah, as I said that even if tournament size of is of 2, is of 3, is of 4, okay, if it is not only one, if it is one and you have only one solution, then it will have one copy. Now if you are having more tournament size, maybe 2, 3, 4, whatever, the worst solution will have no copies, have 0 copies, whereas the best solution will have the number of copies which is equal to the number of tournaments, right? Because in every tournament the best should win, and other copies whatever is there, it should have, it will vary from 0 to the number of tournament size or number of tournament selection whatever you are doing. Okay, so the best solution will have 3 copies, okay, and the worst solution will have no copies, that is 0 copy. Okay, next question is, suppose a solution in a population is this. So a solution is given, a random number is generated to determine the mutated bit of the string, and the fourth bit is selected to mutate the solution. Okay, so we have 1 0 1 0 1 1 1 1, and you are selecting the fourth bit to mutate the solution. The solution after mutation will be, so what we'll do, we'll change this to 1. So 1 0 1 1 1 1 1 1. So how much you are getting the solution? 1 2 3, sorry, 0 1 2 3 4 5 6 7. Okay, so you'll just calculate. I'll also calculate. It will be 2 to the power 7 plus 2 to the power 5 plus 2 to the power 4 plus 2 to the power 3 2 to the power 2 2 to the power 1 and 2 to the power 0. 128 plus 64 plus 30, sorry 128 plus 64, 32 16 8 4 1 and 2. How much we are getting? 120, sorry, 128 plus 32 plus 16, 191 I think, right? But I don't think we have the answer for. Okay, we don't have to convert, the answers were in binary thing only, sorry. Okay, so do we have the correct answer? Okay, so we are changing the fourth bit from the right hand side. Okay, so we are not changing from the left hand side, we'll go from the right hand side only. So the fourth bit will be this, sorry, we don't need the digits because answer is in. So the solution is 10101111, and as we are moving like this, to the power 0 to the power 1 in that case, we'll just change this and we'll get solution, because we'll change this 1 to 0 10100111. The correct answer will be B. Okay, that's it. I thought we have to change. Fine. This is clear, right? Okay, we'll move to the next one. The next question is the decoded value of the binary string. This is how much? It's simple. Let's do it. To the power 0 1 2 3 4 5 6. I'm getting something like 119. Okay, so the correct answer will be B, that is 119. Okay, I hope this conversion and all are clear. Okay, so the next question is, the genetic algorithms do not require the gradient information of the objective function or the constraint function. As we said, we don't need any, even if we don't have the knowledge for the function, we can use the genetic algorithm. So first one is not required. The evaluation of the Hessian matrix not required, because we are going for the genetic algorithms and all. Starting point to the start the iteration, not only one value, but we are considering one population. So we do not require any of these. The correct answer will be all of the above, and that's it. Okay, if you have any question, you can just ask, or else I'll just stop it here. I'll upload this PPT and the YouTube video also. Okay, so thank you. I'll stop it here.